Does anybody have homework questions? In 7.1, we're looking at the Sierpinski triangle and picking the largest figure within the Sierpinski triangle that looks like the whole Sierpinski triangle. So if you pick the largest figure, it'd be one of these three that are this size. They look like the whole Sierpinski triangle. There's that sense of self-similarity that fractals display. Well, the question is, how big is it compared to the original? When they say how big it is, they're looking at its width. So if you took a ruler and measured this length across the whole Sierpinski triangle and compared it to this length, this sub-figure is 1/2 as long as the whole length. So that's why the answer is 1/2 there. Any other questions? Let's continue on then with the fractals we've been looking at. The author asked how you can turn a triangle into a snowflake, and we worked on that with the Koch curve. I was going to show you the Koch snowflake on Wikipedia. So the Koch snowflake is made by taking 3 Koch curves and laying them in a triangle. So you start with a triangle, you make your stage 1, stage 2, stage 3, and so on. And as you make a Koch curve on each of those 3 lines, you get the Koch snowflake. This picture on Wikipedia is to show the infinite detail that a fractal has. As we zoom in, we see the same shape over and over, even as we zoom in. We're going to look at sketching another curve today. We're going to look at making the Sierpinski triangle. So the life lesson in this section is to explore ideas by carrying them to the extreme, because that's what fractals do. We take a process and we repeat that process over and over again. So we'll do that now with the Sierpinski triangle. And I do ask that you draw a Sierpinski triangle on a quiz, so take this opportunity, please, to make sure you're able to do that. So we're continuing in 7.2 with the Sierpinski triangle. So stage 1 is a triangle. If you have your compass, you can use that to draw a triangle. If you're using a ruler, you can use that. If you don't have a ruler, will you please take a piece of paper and make your own ruler? Okay, label it like this, because we'll be using that later on as well. So if you take a piece of paper that you label the lines from 0 to 14, okay? Homemade rulers. So I'm going to make a triangle 4 centimeters on a side. You could use 4 line lengths. If you have a compass, that's easier. If you don't have a compass, then you're trying to find the point where 4 centimeters meets up from both sides. So that's stage 0 or stage 1, depending on how you refer to your stages. On a quiz, I would just give you the first stage and say, draw the next 2 stages. So we didn't have to worry about if it's labeled stage 0 or stage 1 to start. Now we made the Koch curve by shrinking down stage 1 and putting it over the initial line segments of the stage 1. In the Koch curve, in the Sierpinski triangle, we're going to remove material. So we're going to remove the middle triangle. So go ahead and draw the triangle you just drew again. So fractals repeat the same process over and over, and our process this time will be removing a portion. So we're going to find the middle of each of the line segments you used to draw your triangle. So I made my line segments 4 centimeters, so the middle will be at 2 centimeters. We're going to connect the midpoints of each edge of the triangle. That creates a triangle pointed downward in our original triangle. So this triangle pointed downward is removed. It's taken away. So what you have left here are 3 triangles with an empty upside down triangle, an empty triangle pointing downward in the middle. And that's your next stage. Now you don't have to think of this building this next stage as removing the empty triangle. You could think of it as stacking 3 stage zeros in a pyramid, right? So if you stack 2 stage zeros in a pyramid, you have the stage 1 in that fashion. In fact, stage 2 then we would take 3 of these and stack them in a pyramid, but it looks the same as if we take an upside down triangle out of each right side up triangle. So let's draw the next stage. We'll take an upside down triangle out of each of the 3 right side up triangles. So we're finding the midpoints on each of the line segments making our triangle and connecting those to remove the center. We'll go ahead and now make upside down triangles, or triangles pointed downward, in each of these 3 stage 1 triangles. So since we were making little triangles that were 2 centimeters each, now we're marking off at the 1 centimeter mark. You can think of this as removing the pointed down triangles, or you can think of it as reducing stage 1 and taking the reduced stage 1 and stacking it up so that there's 3 stage 1 stacked up. So I'll color in the space that remains. And that will be stage 2. We could keep doing this for a very long time. Let's just do one more, okay? But maybe we'll be a little less precise when we draw the final stage, and maybe just eyeball that last stage. So the first couple stages aren't too bad to draw, not too tricky. But a ruler does help. If you don't have a ruler, it makes it a little harder to make sure you're doing everything neatly. We're going to see another way to make the Sierpinski triangle at the end of this section, which is related to chaos. How many of you have read anything about chaos or ever learned anything about chaos? So chaos theory became popular probably 2 or 3 decades ago. I would say 3. My aunt, who worked in Wall Street, called me up. She wanted to know what I knew about chaos theory and the stock markets. So chaos theory is involved with the idea that little tiny changes can make huge differences when you perform many operations. That's why your author discusses chaos theory in this section of our textbook, because chaos theory is involved with multiple iterations of a process, and that's what fractals are also doing, right? Multiple iterations of a process. So it turns out that you can have significantly different outcomes when you're doing a process over and over again, depending on just the smallest amount of rounding.
Is this our in class?
There is not a class activity to hand in today. Our class activity for 7.2 was the Koch curve, and I think you handed that in on Wednesday. I do want to make sure that you know how to do this, though, so I'll just take a little walk around the room and see if everybody's getting this. I always want to make sure you know how to do the things that are on a quiz, so that you're not caught unawares on a quiz. So I'll just walk around, and our tutor can help walk around too if he doesn't mind, and we'll just make sure you have the empty spaces where you should. So you can think of building these stages in the Sierpinski triangle as reducing the stage before and stacking it up in 3, or you can think of it as removing the center area. We have another Sierpinski shape called the Sierpinski carpet. This is from chapter 1. We'll actually look at this shape again later on in chapter 7. So this time, instead of starting with a triangle and removing, there's a square, and the center square is removed. When you remove that center square, it creates these implicitly these 8 squares on the outer edge. And so in each of those 8 squares, you can remove the square. And then that creates 8 little squares in each medium-sized square, and you can remove each of those 8 centers, and you can keep doing that. So this idea of removing the center shape carries out to many different shapes, including the Sierpinski carpet. Another way to make fractals is with photos. So here we have pictures of your authors. And you can take the picture. Now you should do this for Mother's Day. Your mothers would like this a lot. Okay. Take your picture of yourself, not your authors, and shrink it down. They shrunk them half as large, half as wide in width. And then they placed them in a set of 3 at precise angles. Then they took a picture of that and shrunk it down half as wide. Now, this picture then getting shrunk half as wide, to be a fractal, it needs to be placed in the exact same positions as these 3 angles. So here's that being done. That was a fairly precise way. All of these pictures end up being the same size. You don't have to do that. So here we take the same picture of the authors, but this time make 3 different size shapes. So different proportions when we shrink them down. And instead of placing them evenly, they're placed one on the bottom right, one vertically above it for the smallest one, and then the largest one is set at an angle. So if that's the iteration process you choose, then you stick with that. That's the idea behind a fractal. You stay with the same process over and over again. So this time, this image is shrunk down to the same 3 proportions as the first iteration, and the pictures are then placed in the same relationship to one another. So you keep with the same process over and over again. Now, if you're giving this to your mother for Mother's Day, don't shrink it down as much as they did, right? Because then you can't see your lovely face anymore. There's a famous fractal called a Barnsley fern. So we're going to look at how the Barnsley fern's created. The Barnsley fern is made by taking the original shape and shrinking a little bit, and then 2 that are fairly small but not quite the same, and 1 twig. Then those are placed in a particular relationship to one another. They're placed in this relationship. And then that's shrunk into the same 4 copies and placed again in that relationship, and shrunk again and placed again in the same relationship with one another. And if you do that enough, you get this shape called the Barnsley fern. It turns out that if you use these twigs, you'll get the Barnsley fern. Or if you use a car instead of twigs, you still get the Barnsley fern. Why do you think that is? Why can I start with a twig, this shape, and get a Barnsley fern at the end with repeated iterations? Or I can start with a car and get a Barnsley fern. Why would the very different starting images yield very similar end images? Yes?
Because it's small enough so it doesn't even matter.
Yeah, exactly. Because you get so small it doesn't even matter. So I'm going to show you the Barnsley fern generator that I have linked on the Canvas homepage. And that doesn't use cars or twigs, it uses points. So this is linked on the Canvas homepage. And if we start with just 5 points, you can see real tiny little points here placed where those twigs were. This is the math that's going on behind creating these iterations, and you can fool around with that too if you like to get involved in math. So this is multiplication and addition of matrices. Anyway, if we have 50 iterations, there's 50 points. If we have 500 iterations, now we're starting to see a shape of fern shape. If we have 5,000 iterations, or 50,000 iterations, or 500,000 iterations. So the more iterations we get, the more it fills in. And it didn't matter that we started with a point instead of the twigs or the car. We still get the Barnsley fern when we do the same iterations over and over again. So that idea of it not mattering what we start with, we can see in your textbook. Here the Sierpinski triangle is formed with different shapes. So we created the Sierpinski triangle out of triangles, right? Okay, but here instead of stacking triangles up, they stack up blocks. Here they stack up dots. Here they stack up this kind of a curvy initial. And here they're actually stacking up Sierpinski triangles themselves. So they're going to stack them in 3. And we get this shape that is different for each image, except the Sierpinski triangle continues to look like itself when it's stacked in 3. Then we do the second copy. They still look pretty different from one another. We do the third copy, starting to look quite a bit alike. When we get to the 4th and 5th copies, they all look pretty much alike, except this one, and I think that's just because it's sketched at a larger scale. So it doesn't really matter our starting image, and you'll see fractal generator is often done with points for that reason. We're going to look at another way to generate a fractal, and that's using an overhead. So I'm going to give all of you an overhead that looks like this, and we're going to take our rulers and markers and go through and do these steps with it. So here's the steps that we're going to take. I'll give you an overhead, and then we'll work it out together. Online students, you can print out the triangle, but I didn't have a way to give you a transparency. But you can print out the triangle and try this along with us. So I'll just hand these out. So again, if you don't have a ruler, please make a ruler out of paper, or extra piece of paper. Oh, I forgot to keep one of those for myself. If it's not enough, you might have to work in pairs. So you'll need a dice game as well. If you don't have a dice, which I don't know why you would, can you please go to random.org or some other app and get a dice? So I would use random.org. This is going to generate the Sierpinski triangle. So if you're putting points down and they're going in these blank spaces, you're doing something wrong, and please stop and we'll make sure someone comes around and help you. So you notice we have big blank spots here, 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 and here. We should get no points being drawn in those blank spots. So I'm having you do this on transparency so we can share our points together. I didn't think you'd want to sit here and do 500 points, so if we put all of our points together, we should get a good representation. So remember I was talking about chaos and how chaos has multiple iterations, and that's why it's in the same section as fractals. You can kind of see that relationship a little bit when we use randomness, the dice, to help us draw these fractals. Okay, so we're always moving halfway between the point we're at and the dice throw. We're always moving halfway between the point we're at and the dice throw. So this example, we're all going to start with the initial point here, and then if you throw a 2 with your dice, you would measure halfway between the 1 and the 2 and put a point. So that's your new starting point. So now you're here, and this example throws a 2 again, and so they end up halfway between here and here with their new point. Now they throw a 3. So this is their new starting point, and they go from that starting point to the 3. They measure with the ruler and put a point halfway. That's their new starting point. This time they throw a 1. So they take a ruler and measure from the point they're at to the 1 and draw a point. Next they throw a 2. So they go from the point they're at here and they measure and put a point halfway. And they keep doing that. So we're going to keep doing that as well. I guess I'll leave this up and walk around and see how you're doing. So use your dice throw and your ruler to help you plot these points.
How do you want us to draw these?
Oh, you probably need markers, huh?
Yeah.
I brought markers. I did remember markers. Okay, so I'll walk around and see how you're doing, and then hopefully we'll be able to collect these all together and see something nice. Do you need a marker? Nicholas, did you walk around and help people too? Does anybody have markers? Raise your hand if you're stuck, or throw something at us. You roll the same point you're on, you go for it.
I think so. These don't really stay on the it disappears.
You can use a pen if you feel like your marker's just kind of washing off. Okay. Do you have a ruler then? So what did you draw?
I don't have any dice.
So you use it on your phone or on the laptop, go to random backwards or some other place to get a dice. You can use my marker if you want. Well, this is oh, okay. You also, if your dice generator is coming up with 2, then you can use the first dice and then the second dice. So it's like the so where are you at?
So if I choose 4 in there.
So,
How do you know that?
oops, I don't draw a line. No, just one point.
Well, it comes off easy enough.
Okay, okay. Yeah,
So
so.
if I'm thinking, hold on.
Okay.
But right now I'm on. Okay, what's up? Is that almost, you want to get over here, you want to get over I see it. So what do you want to do?
Well, this one was 3, this one was 5.
Now, is it like a 5? This is your starting point, you put the ruler to their 5. And then you measure it halfway between the two.
Oh, so it'd be,
Yeah, but get it exactly, because otherwise you're gonna get a little. Actually, there should be one there.
Well, like, I don't see how it works.
Here, let's measure this.
Just because I say 4.
We should center up and
I
center.
got the same number, 4.
And you go 5.
Okay, so here it shows like 5. Is it at so
4.75, so
5 times in a row.
4.75. You like 2.3.
So whichever number is. Okay.
So I think it might be a
Okay,
little
and
bit,
then now what?
a little bit smaller than before. So can you put it
So how many times is there?
the third one? Yeah.
Okay.
All right,
So
and then we measure from there to 5.
So I'm always starting here. Okay, what is that, the 6? So go this way.
Okay, so then
This is right there.
now that's your point. If the pen works better, use the pen. So you keep getting 1s and 4s? I mean, one to go back and forth here? Okay, so. Yeah, you should probably have to put white paper under your,
I don't really know where I'm supposed to
transparency.
draw.
You're, well, first, you're not supposed to draw anything.
Oh, so.
There it is.
Here, and then move that one. And then in here, you have that one, and back. Okay, and up again. This
You're
one,
supposed to be using a random number generator.
Yeah.
I did that one without the ruler.
And you start
Oh, okay.
at
And then start over from there.
1,
Hmm.
and then whichever number you roll, you put a dot halfway between your current point and whatever number you roll. So if you rolled a 5 or 6, you put it right here. And then say you rolled a 5 or a 6 again, you put it right here. Say you'd roll a 3 or 4 after that, you'd go about here. Does that make sense?
Yeah. It's like along the yeah. Yes, and then you're right along there. Yep.
I have no idea what I'm doing. These aren't showing up, so.
Okay, we switched to a
I
pen.
just drew. The pens don't work either, I tried everything.
So
So I just drew random dots.
Okay, so random dots are gonna mess up my, you're gonna throw off my groove, okay? So,
Okay.
so can you use your finger and erase it or
Yeah.
an X or something? Okay, then we'll see if we can get it.
Like I got the first view and then I got confused.
You especially don't want anything in here, because that's gonna be,
Okay.
that should end up being blank on the surface.
Oh, okay, I understand.
So, so you don't have a Kleenex, do you? So that's fine. Get that one. Okay, thank you. Okay, so what was your first dice throw? One?
No, the results are.
Oh,
here.
5.
Yeah.
Okay. So can you put your ruler from the first point to 5?
Should I do inches or?
I think centimeters are easier to divide into.
Okay.
So the 5's over this way.
Alright, so like parallel.
So don't put a point at the 5, and so measure from there to the 5.
Okay.
Okay, so how far is that?
12 centimeters.
Okay, so you do 6. So that's your new starting point. And you can roll another dice.
And then where do you go?
So that's 3. So So this is where the 0 on your ruler goes, and your end of your ruler goes here. Do you want to know that, Mike? What does that mean? 10. Okay, so you put a point at 5.
In the middle of the triangle?
That's pretty close to the middle, but that's where it goes, so that's where it has to go.
There's nothing supposed to be in here.
I think it'll be far enough up, it'll be okay.
Okay. And just keep doing that.
Yeah.
Okay.
So now you're going to 4. How's that going? Okay.
Like how we drew lines the first time.
Okay.
How many points do you want us to?
I'd like to get 10 out of everybody. Do you mind showing me what you're doing?
I, for choosing to do anything, from point to roll the dice to it, like halfway between what you did.
Yeah, so it must be a thing in French that threw it off a little bit. So that's an example of how a tiny little bit off and then reiterate over and over can get somewhere else.
There you go. That's just all I need.
Okay. Okay, well, I'm going to start stacking these up then. If you have a pen, I'll take yours and start stacking it with my others. Perfect, so I'm going to have to get some bigger.
I keep getting like the same 2 numbers.
Doesn't change much if you keep getting the same 2 numbers for the
I keep getting the same. So I don't know if you want it.
Okay, we'll take what you have.
Literally, yeah.
See that? Well, somebody has to do the edge.
And this is showing like chaos.
This is showing another way to make this fractal, this Sierpinski triangle. Thank you. I got one off. Any more? Two more. Thank you. Oops, excuse me. So we have the way to form the Sierpinski triangle using the dice and the drawing the dots, try and line these up perfectly. And the dots only end up getting drawn exactly where there should be a point in the Sierpinski triangle. So I tried to line that all up so we'd have 500 dots, but we don't have enough students to do 500 dots. If we did have 500 dots, then we'd have this one that's computer generated, we'd have this type of look. And then if we had 1,000 dots, and if we had 1,500 dots, we would have this type of look. So this process that you're doing to draw the Sierpinski triangle can also be made with random dice throwing and marking off points. Some of you who were ending up getting points where there should be blankness in our Sierpinski triangle, we're experiencing the effects of what I was talking about a little bit earlier. Chaos theory is when you do multiple iterations over and over and over, and you can be off by just the tiniest bit, and your end result will be very, very different. The more iterations you're doing, the more you'll be off. And that, I mean, I'm talking about the difference between rounding to the 1,000th place and the 10,000th place. So that's why when we do computer models that have multiple iterations, you can have huge discrepancies depending on what your initial starting point is. And if your initial starting point is just 100th different from the person next to you, who's using rounding to the thousandths, you can get very different results. Fractals have real-life applications. I know you like to have applications. So I have brought you some manufactured items that use fractals. Here's some engineered fractals to help solve the challenge of fluid transport. So they ended up using fractal patterns that mimic our blood vessels in our lungs. And that was to dissipate heat in computers. Here we have a 3D fractal, and this is used to distribute and collect fluids as well. So it's to spread fluids throughout a volume in a way that spreads out the fluids without just pouring them all in one spot, to just not have all your new fluid that you're adding be concentrated in one spot. So these are fractal fluid mixers. So they've been used for fields like high precision epoxies, manufacturing sugar, and chromatography. Or it can be used for sampling, right? Because in the same way you don't want to necessarily dump all your fluids in one area when you're mixing, you don't want to sample all your fluid in one area. So you can grab samples using these three-dimensional fractal images as well. That's as far as we got in our first class, so that's where we're going to finish up today. I hope that you can all draw a Sierpinski triangle now, and I hope you feel like you understand more about fractals and the iterative process that makes them. See you on Monday.